All right, workshop students, let me continue on here with the next problem. If you watched me just solve the week 6 quiz number 3, now, and I guess this is the answer to all that. Let me get rid of this one and then move on to week 6 quiz number 4. Okay. And this one has an object going in a circle, or rolling in a circle, actually. Oh, slides. Good. It says slide, because we really don't want to do things rolling quite yet. That's coming up. And those tend to be hard problems. But okay, anyways, a marble slides around a frictionless spherical bowl moving in a horizontal circle at a constant speed as shown in this image. So kind of got this thing rolling around in a bowl, okay. By the way, notice the circle of the path, it's horizontal, and notice this is the center of the circle, but up here is the center of the bowl. And looking at your answers, this could easily get confused, which one is which. Here it says, check all the answers below which are true statements, and there may be more than one correct answer. All right, so again, if you saw the previous video or any of my videos, I like to say when you're doing this, you should do 4 steps. First one is a good physical picture. Second one is free body diagram. Next one is write out the equations. And the next one then is solve the equations. Now, again, this isn't a full problem, so I'm not sure we have to do all 4 steps. But at least let me kind of follow that direction. And the first picture, a good physical picture, I probably don't need to do too much because the author of the problem actually gave me a diagram to look at. They talk about a bowl and then the ball rolling around in a horizontal circle around the bowl. And because of that, I can kind of see where the center of the circle is, as well as where the center of the bowl is. And it looks like capital R is the radius of the bowl, not the radius of the circle. I don't know if I'm going to need this, but it looks like the radius of the circle would be capital R, and I would want opposite of theta, so sine theta. Anyways, I think that maybe that's a good place to start here and say, okay, I got a good physical picture. So I've done step 1. Now I can move on to step 2. All right, so step 2 is this free body diagram. And like I said in the other videos, don't cheat yourself out of these steps. If you skip one of these steps, it's like going up a staircase. It's just extra hard if you skip one. And if you try to skip 2, it's probably impossible to actually achieve the goal of getting up the staircase. So each one builds on itself. And so let me just kind of draw the object. So there it is. There's the marble. And let's draw the forces on the marble. And again, one of those will be gravity, and gravity will pull straight down. So I always say draw gravity first, and then everything touching it. And coming back to the step 1, the physical picture, the only thing touching it is the edge of the bowl itself, the surface of the bowl. And so that means this surface could be looked at as 2 components, one being the normal and one being the friction. But for this problem, they said it was frictionless. If we jump back to the one we did just a moment ago in number 3, it did have friction, so we said there was a normal and a friction. And it almost sounds like there were 2 things touching it, but it's not. It's one thing, it's the incline, and these are the components of it. So on this case, then, the normal would be directed like that. And I'll use the little n to represent the normal force. And there wouldn't be any friction. And then I'm done. This is the free body diagram. These are the only 2 things acting on it. Okay. So then if I continue on here, I would say now I'm ready to go and write out the equations. Okay. Now, as I often say in my help videos here, for something like this, I would divide your paper into two pieces, X and Y, because then there is the sum of the forces in the x direction, which equals to mass times acceleration in the x direction, and the sum of the forces in the y direction. And so this is, right now, Newton's second law of motion. Now, my highly recommended hint here is to set up a grid. And so I'll do that in green. Set up a grid so that the acceleration is along the x-axis. And I like to do that because when you do, this right here just becomes a. You don't have to have a cosine or sine of something. And then this one over here becomes 0. And it's nice to have one of your equations equal to 0. It's also nice not to have a sine or a cosine here. Okay. Now, what that might mean, though, is you might have to have a non-traditional axis, and so that's kind of the price we pay. It also means you got to do a little bit of physics of what is the direction of the acceleration. And one of the things that hopefully you learned in this chapter that, I'll put it up here, if an object goes in a circle, let's say it's right there, the acceleration is towards the center of the circle. Or if it was up here, it would be towards the center of the circle. If it's over here, it's towards the center of the circle. Or if it's down here, it's towards the center of the circle. So I like the phrase towards the center of the circle because I'm not saying X or Y. I'm just saying towards the center of the circle. And then you can set it up however you want. But if I take this back to my free body diagram then, and I even go one step further back to my physical picture, the center of the circle it goes around is this point here. And so on my free body diagram, that would look right here. And so I like to put a little C there and say, okay, that is the center of the circle as it goes around. It does not go around a center that's down here at the bottom of the bowl, nor does it go around the center of the bowl. And because of that, I like to make my x-axis pointing towards the center. Now that's kind of like the traditional one, other than I am now calling left positive. I'll stick to the y up as positive. But these, of course, have to be perpendicular. So once you choose the x, the y is determined, although I guess you could go up or down depending on how you want to do it. So here I have what we would call a left-handed coordinate system because instead of having the x positive to the right, we have x positive to the left. But not, again, worrying about left hand or right hand or fancy words. I'm just going to say I have a grid, and maybe the bad part is it's non-traditional, but only a little non-traditional. But the best part is right here, that the acceleration will all be in the x direction and none will be in the y direction. That's the real main point here. Okay, so then I could even go one step further because I know v squared over r, and r being the radius of the circle, so come back to my physical picture, this would be r sine theta, is what I would get so far out of these two equations. Now again, maybe I'm overdoing this problem. I just thought it would be a good chance to kind of do a little mini lecture and kind of help you learn. But I don't think we even have to go through all these equations because they're asking us word stuff that we could probably answer right now. But for completeness, I'm just going to finish this off and point out then that as I write out these equations, now I would look at my forces, and I'll just look at, say, the gravitational one first and then the normal one, because the gravitational one would fit right here where I would say it is all mg in the negative y and none in the x. And so that's the x and y component of the first force, the force of gravity. Okay. Now, by the way, you might have been tempted to make an axis that was tilted because that's what we did in number 3. But I want to emphasize, I didn't change my thinking. My thinking always was put the x-axis in the direction it accelerates. And so in this case, since it moved down the incline, that was the direction of the acceleration, so I made an x-axis down the incline. This problem is different in the sense that it's going in a circle. Yes, there still is a slope here, but that's not the reason I picked my axes. I picked my axes in the direction of the acceleration, and since it's going in a circle, the direction of the acceleration is towards the center of the circle, which in this case is horizontal, which is one of the questions here. Now, as I, again, kind of overkill this problem, I will just point out that that angle there would be theta, so that when I look at the harder of the two forces, the normal force, there would be an x component, and the x component here would be opposite of theta, so it would be normal times sine theta for the x, and for the y, it would be normal times the cosine of theta. And again, I don't know if we really have to solve this, or maybe we do. I kind of see an answer here, but if you look at the solving this for the normal force, and so going on to step 4, I should say. I get an equation for the normal force that is mg divided by cosine theta. And let me point out the same thing that I said in problem number 3 is don't assume that the normal force is always mg. Here was mg times cosine theta. Interesting in this one, it's mg cosine theta. Don't try to predict what they are. Like I said, just write out the forces and solve the math. And that's what it comes out this time. And then, of course, over here, I would have normal force sine theta. If you wanted to keep working on the math, I guess I could replace normal force with mg over cosine theta. And then I have this sine theta, and then I have this mv squared r sine theta. Maybe I'd cancel off an m. Maybe I would then write this as g tangent of theta equals to v squared over I'll just put r sine theta. Tempted to call that little r again, because I know you saw this in your textbook, something going around a circle on a slope, you know, a banked curve. You have g tangent theta equals v squared over r, and the r was then the radius of the circle, whereas this is the radius of the sphere. So that's kind of the difference. Anyways, again, I think I'm overkilling it, but I hope I'm illustrating these 4 steps. I'll just say it again. Good physical picture leads to a good free body diagram, which leads to writing out the equations, which then leads to solve them. So don't try to just guess what the normal force is. Solve it. And the easy step, believe it or not, this is supposed to be that easy. Right here, just write out the equations and then solve. So step 3, step 4, write out the equations, solve. And they really are that easy if you have a good picture here. And you get a good picture here if step 1's done right. All right, well, finally, let's answer this. Okay. So the answers would be, and it looks like I printed it kind of funny because it looked like it double printed option number 1. But here it says the normal force on the marble points towards the center of the sphere. The sphere, yes, it does, right? This goes back to this picture, maybe back to the physical picture. It's pointing perpendicular right towards the center of the sphere. So this should have been checked. So that's probably why this one got marked wrong. Okay. Now this other one, the normal force on the marble has a magnitude equal to its weight. No. Let's see, I went through this, right? It's actually more than its weight because cosine theta is always less than 1. So it's mg divided by something less than 1, which makes it a normal force more than mg. So that's another reason this question would be wrong. So somebody put a check mark here. So that should not be checked, the normal force. But like I said, it's the thing that I wanted to warn you about. It's common to just say, hey, normal force is mg. No. I'm going to say it again. Just write out the equation, solve for the normal force. I just did that here, and I did it here. And in both cases, the normal force was not mg, and it was even something different. So don't try to guess what the normal force is. Work it out. And then the third option, the marble's acceleration vector points horizontally. Yeah, that's something we needed to know about objects going in a circle. That's our decision for setting up the grid the way we did. And so that one should be checked and was checked. And so that one is correct. All right. Well, again, a little overdoing the problem, but hopefully helping you with all the other problems that are just like this, because I can guarantee that you can solve every single problem with these 4 steps. And I tried to illustrate it in number 3, illustrate again in number 4, and then on the next video I make, I will illustrate it on number 5. All right. Till next video.